Look around. Try to find a colourful object and focus on it. It doesn't have to be anything interesting, just something that isn't black. Perhaps a red pen or a brown desk, or maybe you have one of those green parrots as a pet, whatever. That object, according to Carl Hempel, confirms the theory that all ravens are black. This seems crazy. How could a red pen have anything to do with black ravens? Well, it is crazy, but the Ravens paradox is famous for a reason. Before we get into all that though, we should discuss Jean-Nicot's 3 criterion of confirmation, and why they are so important to paradoxes like these, paradoxes of confirmation as they are called. If you have a hypothesis that generalizes, like saying, my hypothesis is that all trees grow, for example, what you're really saying is, if X is a tree, then X is growing. This goes for any generalization, and for clarity, we'll go with, for any object X, if X is P, then X is Q. So for any object, if that object is a tree, then it's growing. Here's where Nico comes in. He says that for all statements like these, statements where if P then Q, you can be sure of 3 things. 1, the occurrence of P and Q helps to confirm the hypothesis. 2, the occurrence of P without Q disconfirms the hypothesis. And 3, the occurrence of Q without P is irrelevant. So, using our tree example, for our previous hypothesis, all trees grow, if I see a growing tree, then that supports my hypothesis. If I see a tree that isn't growing, I know my hypothesis is incorrect, and if I see something that is growing but isn't a tree, it doesn't matter, it's irrelevant. Now that we know about Nico's criterion, we can move on to the next step, the logical rule of contraposition. This can be easily understood by taking our hypothesis, if P then Q, and flipping it on its head to make, if not Q, then not P. Although it may not look like it, these are logically equivalent. They pretty much just mean the same thing. We can see this by using our tree example again, saying if X is a tree, then X is growing, is the same as saying if X isn't growing, then X isn't a tree. If it's true that all trees grow, then when I look at my desk and see that it isn't growing, I can be absolutely sure that it isn't a tree. And if I see a tree, I can be absolutely sure that it is growing. Contraposition is an accepted rule of logic, and pretty much impossible to refute. Of course, trees grow very slowly, so if I saw one, I wouldn't actually be able to tell, and dead trees don't grow at all. But for the sake of argument, we can just ignore that and assume that they grow really fast and dead trees don't exist. Now that we have Nico's criterion and contraposition, we can mash these two together to finally get to the Ravens paradox. According to Nico, seeing a growing tree helps to confirm our hypothesis that all trees grow. But due to contraposition, because all trees grow is logically equivalent to all non-growing things are non-trees, or anything that doesn't grow isn't a tree, this means that when you see something non-growing that's also a non-tree, it too confirms our hypothesis that all trees grow. Therefore, when I look at my desk, which isn't growing and isn't a tree, I am supporting the hypothesis that all trees grow. As you have probably realized, when we replace all trees grow with all ravens are black, we get the Ravens paradox. Seeing something non-black and a non-raven, like a red pen, supports the hypothesis all non-black things are non-ravens, and therefore all ravens are black. Now, we take a step back and put ourselves into the mindset we had when we first heard the statement. It's ludicrous. Seeing a red pen surely can't support the theory that all ravens are black, and thus the paradox. Sainsbury said all paradoxes are essentially arguments, and this one is no different. Premise 1, Nico's criterion. Premise 2, contraposition. Conclusion, seeing a red pen confirms all ravens are black. To attempt to solve this paradox, we can do one of 3 things. We can either reject premise 1, reject premise 2, or we can simply bite the bullet and accept the conclusion. As previously stated, premise 2, contraposition, is a basic rule of formal logic, and rejecting it would just lead to a bunch of problems. It would be like trying to prove that 1 plus 1 doesn't equal 2, it just won't work, so we'll leave it alone, it is true. Now, we're left with either rejecting Nico's criterion, or accepting the conclusion. For Hempel, the best option is to do just that. Bite the bullet. He argued that it's simply not paradoxical at all. Instead, it's a misconception about what confirmation really means. When we have a generalization like all trees grow, the things that back up this hypothesis are the individual instances of growing trees. We say that these instances act as evidence, or they confirm the hypothesis. But what do we really mean by confirm? On first glance, it seems like we should be able to find all of the trees in the world, see that they're growing, and then boom, our hypothesis is proven correct. It has been confirmed by the individual instances. Bertrand Russell, however, disagrees. He says that for a generalization to be truly confirmed by its instances, it must be logically proven true. The key thing to keep in mind here is that Nico's criterion, and therefore the paradox, are only concerned with the instances. They are the only thing in play when we try to confirm our hypothesis. So to logically prove our hypothesis, normally we could simply go from tree to tree, noting that they are indeed growing until we find them all. Then we know that our hypothesis is correct, all trees grow. However, the problem here is that this method uses the individual instances and also the knowledge that we have found all of the trees. To make this a bit clearer, we can put it into logical form. Every tree is an individual instance. We'll call it T. So the first tree we find is T1, the second is T2, the third is T3, and so on, until we find the last tree, which we'll call T3 trillion. When we write this down, we get T1 grows, T2 grows, T3 grows, yada yada yada, T3 trillion grows. From the knowledge of these instances alone, we cannot conclude that all trees grow, because we do not know that we have found all of the trees in the world. While it is true that we have found all of them, we're not allowed to use that knowledge in our argument, because we are attempting to prove that all trees grow using only the instances, without any extra information. Therefore, we can conclude that trees 1 to 3 trillion grow, but we cannot conclude that all trees grow, and this means that we can use individual instances as evidence for our hypothesis, but not as logical proof. So, when we bite the bullet and accept the conclusion, we're really saying, yeah, sure, a red pen can be used as evidence for all ravens are black, but you can never prove that all ravens are black using red pens, and so it doesn't matter, it's not a paradox. We've now discounted rejecting premise 2, and we've also considered accepting the conclusion, so we can now move on to attempting to reject premise 1, Nico's criterion. To do so, we can look at Goodman's GRU paradox and determine how to use it to thwart Nico. The term GRU refers to something used in Goodman's new riddle of induction, first set out in his 1955 book Fact, Fiction, and Forecast. It means something, quote, that is examined today or earlier and found to be green, or is not examined before tomorrow and is blue, unquote. The reason it's called the new riddle of induction is because the existence of GRU causes lots of problems for induction. If I work in an emerald mine and find that every single emerald I've ever found is green, it's natural to think, through induction, that every emerald tomorrow will also be green. However, it's also true that every emerald I've ever found has been GRU, and so it stands that they should still be GRU tomorrow, in which case they would be blue. This leads to the conclusion that tomorrow, emeralds, and everything else green for that matter, will be both green and blue at the same time, a clear contradiction. Therefore, induction as we know it has a big problem. Nico's criterion plays a massive role in the new riddle of induction because, as we've discussed, they say that the occurrence of P and Q confirms the hypothesis if P then Q. If X is an emerald, then X is green tomorrow, and if X is an emerald, then X is GRU tomorrow. And as we know, if X is GRU, then X will be blue tomorrow. Therefore, given the existence of GRU, Nico's criterion must be false, because it leads to observations of green emeralds confirming a contradiction. Goodman himself attempted to solve this problem, introducing the concept of entrenched and unentrenched predicates. He said that a predicate can only be rejectable, that is, can be used in induction, if it is entrenched in a language. An entrenched word is one that is commonly used or accepted by a community. So, for example, the word brick is entrenched, while the word prungle is unentrenched, as I just made it up. So, according to Goodman, I can use induction to say every brick is affected by gravity, but I can't say every prungle is round. Likewise, GRU is not entrenched, so it's not rejectable. The problem with this is that we invent new words all the time, and they can become entrenched. Before laptops were invented, the word laptop didn't mean anything, but now it does. The same goes with GRU. For philosophers, GRU is entrenched. Everyone knows what it means, and it's used a lot when talking about the new riddle of induction. Another option, set out by Swinburne, is that projectability relies on whether the predicate is qualitative or locational. A qualitative predicate is one that does not rely on space and time, so for instance, a shoe. It doesn't matter what day it is or where it is, it will always be a shoe, and it will always have the same characteristics. A locational predicate, however, like GRU, does rely on space and time. Today, a Grue emerald is green, and tomorrow a Grue emerald is blue. Swinburne says that only qualitative predicates are projectable, solving the new riddle of induction. Unfortunately, Swinburne's solution is just as flawed as Goodman's. If we define Bleen as blue today or green tomorrow, the opposite of Grue, then we can simply define green as Grue today or Bleen tomorrow. This makes green locational and therefore unprojectable, which we know isn't the case. Therefore, Swinburne's solution does not work either. A third solution, like Quine, states that it is not entrenchment nor locational predicates that matters, but it is instead similarities and the ability to group things into kinds. He separates natural kinds from unnatural kinds, with only the former being projectable. A natural kind is essentially a group of things that share similarities obvious in the real world. So the kind green is natural, as we can look at grass, emeralds, and cacti and see that they belong together, they're all green. But I can't put the word prungle into any natural kind, because it does not refer to anything in the real world. Grue is also unnatural, as it is only terminology and does not mirror anything. However, Quine points out that often things that look similar are not part of the same natural kind. Take a grey wolf and a Siberian husky, for example. They look similar, but we know that the husky is actually genetically closer to a chihuahua. He says that the term dog, in the scientific sense, is unnatural due to this, but it is still very useful due to science. We still use dog in induction, however, because the layperson knows about the genetic similarities, and so it is natural in that sense. Scientists tend not to use induction because when they're researching, they're interested in the facts, while the layperson is free to say, all dogs have a heart, or whatever. Therefore, Grue is unprojectable, as it is of an unnatural kind and cannot be used in induction. Thus, Nico's criterion stays alive. We can provide evidence that emeralds will be green tomorrow without saying emeralds will be Grue tomorrow. So, because we can either accept the conclusion or accept the natural kind solution set up by Quine, we can see that the Raven's paradox is false. But if it isn't a paradox, why does it seem like one? Hempel says it's because we're too involved. We already know too much about ravens. If we were doing a science experiment to test the generalization all sodium salt burns yellow by burning various compounds to see what color the resulting flame was, it seems much less paradoxical. If we burn an unknown substance and it burns green, when we test it and find that it is copper, this helps us in our investigation. If it had turned out to be sodium and not copper, our hypothesis would have been disproven, and so the fact that it wasn't sodium essentially saves us, and most certainly helps us. When we see a red pen, we intuitively think that it has nothing to do with whether ravens are black, only because we already know that ravens are black, and that a red pen is neither black nor a raven. Thank you.